Afternoon, everybody. Last time we started with DC machine in general, and we stopped at the winding, and we said we are not going to be involved a lot in the way how you put the coils and the rotor and the stator. But just what should we know that we have two types of wind, one called lap winding and the other called wave winding. And the difference between both, in lap winding, the number of paths equal to the number of poles, and the poles, they are on the stator. So if you have two poles, you will have two groups of winding connected in parallel. If you are dealing with lap, you have four poles, you will have four parallel circuits. So if you have four poles, I mean, you have one, two, that's equivalent. That would be the equivalent winding on the rotor if you are using a lap. But for wave winding, doesn't matter the number of poles, you have only two parallel winding on the rotor. And there are reasons for that. Why do you do these types of winding? Obviously, when you have like four winding in parallel, you can distribute the current, right? You can distribute the current, so the current will be higher, the voltage will be smaller. But if you have only two, so you can keep the voltage high and the current low, and so it depends on the application. So that's what I wanted to know about it, and then you can read about how they do the winding. That's a technical part. And now we'll go for what does it matter, or what's the value of knowing this kind of thing. It will help us to find something called the machine constant. What does it mean, machine constant? Every machine has a constant that it can tell you how much voltage will produce, how much torque will produce. To understand that, let's just explain something simple here.
Do you mean how much the machine itself will produce?
Yes, yes, the machine itself, yes, the machine, the DC machine, how much they can produce. Let me tell you why that. How the machine produce voltage. We said that there are conductors, the winding and on the rotor, and we have magnetic field produced by the stator. And then if you want to have motor, so you have to supply current to the conductor. So you have conductors, you have current, and you have magnetic field. The force will be produced. Okay. Well, how much voltage? It depends on the number of turns, right? It depends on the number of turns. So as much as turns the machine has, you can have more voltage. Also, it depends on the number of poles. Do you have two poles or four poles? Maybe you have four poles. You have two poles. So it will affect the magnitude of the voltage produced or EMF produced. So, and also it depends on the speed, how much, or the speed of rotation of the rotor itself. So we know that EMF, if we call it E, and we call it EA because it's produced at the armature of the motor, we call it EA. That means the EMF produced at the armature. And when I say the armature, it means the winding on the rotor. You might wonder, it's a motor. Why it produces voltage? Well, yeah, it's a motor, but once it rotates, so you have conductor rotating, moving inside magnetic field. So you have EMF produced. That's why you call it back EMF. So you'll find sometimes, I mean, it be written in detail, back EMF. All right. So this voltage produced in the motor or generator, because we're going to study both, motor and generator, it will proportion to, number one, to the flux. How much magnetic field you have. Every time you have stronger magnetic field, higher value of magnetic field, you'll have higher voltage. And also it depends on the speed. All right. Faster, more voltage. So what's left? What's left? The number of poles of the machine and the number of conductors. And is it connected lap winding or wave winding? What kind of winding? Because there's one who have two windings, another one maybe will have 4 or 6, depends on the number of the poles. So this one, if you make it equal, so we'll say EA is equal constant, and we call it KA times phi times omega. That's the machine constant that I'm talking about. And this machine constant, as we said, it depends on the structure of the machine, simply the number of conductors and the number of poles. So let me show you now the formula. Oh, before I move, let me talk about the torque. The torque, let me call this one TD, the developed torque, or the torque developed by the motor. So that's its name. And sometimes also they call it electromagnetic torque. It's not the mechanical one. It's before going to the shaft, but it's already produced by the machine. And once we take it to the shaft, so we'll have like some losses, mechanical losses, the bearing, the friction, the windage, all the things. Then we'll have the pure. But this one developed, it's just before the losses, just produced by the machine itself. And it depends on what? It depends on the flux. You have higher flux, you have great value of flux, then this torque produced will be higher. So now we observe that the flux, the magnetic field, and we're going to study when we analyze the machine, it has really a big effect on the EMF and the torque. And also now the developed torque, it depends on what? We know that the voltage depends on the speed. When it's speeding, it means variation of the magnetic flux produce more voltage. But what about the torque? What affect torque? Okay, how the torque is produced? Force up, force down. How the force is produced? Conductor, magnetic field, current in the conductor. Already said the flux. What's left? The current. Because yes, when you pass current, more current in this conductor, then the interaction between the magnetic field and the current will be higher. If you have higher force, you have higher torque. So it depends on the current. So this torque is equal constant. And if you are using omega instead of n, and you are using the same thing here, both constant is the same value, numerically the same one, if you keep it like that. And again, Ka is the same, so it depends on the number of conductors and the number of poles. Now we'll go to a document here. So the equations here is written, and that's the constant Ka. It's equal. I want you to understand what does it mean, because I mean you can use that, both are equivalent. N is the number of turns, P the number of poles, A small it's the number of parallel circuits, and that depends on the type of winding. So if you see lap winding, look for the number of the poles with the same number. Wave winding, just 2. You have only 2 parallel paths. It does not depend on the number of poles. That's all. So, and I wrote here that. So that's EA, the constant that of the machine. What about Z, the number of conductors? What is the relationship between number of conductors and number of turns? One turn going like that has 2 conductors. So obviously, that's why you see here Z divided by 2. All right. So Z number of conductors and number of turns, they are related. Every one turn has 2 conductors. When going in this direction and turn back, come back again. All right. So this or that depends on whatever given in the problem. So that's, I mean, what I want to talk about. And the torque, the same equation here that I just explained, and the same constant Ka. All right. But when I wrote this equation, Ka time flux time omega for the voltage produced by the machine and torque produced by the machine. What is flux? Because there are many terminologies used with flux. This is the flux per one pole. You see the magnitude of flux for each pole, right? So let's now look at one pole. We have 4-pole DC motor, wound with 400 conductors. So that's the first information. So that this number 400 is it's N or Z, it's Z, number of conductors. So we'll say Z is equal to, let's have it.
So Z is your amount of conductors.
Z number of conductors, yes, number of conductors. Yeah, that will be equal to 400. And 4-pole, so I can write P is equal 4-pole. The pole shoe, I showed you last time what is the pole shoe, but let me show you again. It's important, this problem, to remember the whole. Yes, that's a pole. That's a pole shoe. But I got to tell you something. You know, the rotor is like a cylinder. That's the rotor, and it's very important to know the area under every pole shoe. That has length always. That's we call it L. That's the length of one pole shoe, and the area on the, not the area, this curve, you know, this arc on the rotor facing the pole shoe, we call it tau P. Tau P, pole pitch. That's exactly the arc length under it. So if you want to calculate it, that's easy. You got to know the diameter of the rotor. See what's the diameter. And if you have 4 pole, so you divide the circumference of this circle by 4. So it gives you approximately the arc. Because of course, I mean, it's not attached together. There's some kind of space, but if it's not given to you, the space given between each pole shoe, so just divide it by 4, and then you will have the, so how you calculate? Let's do that. If you have the diameter of this rotor, it's a circle, and it's D. So the all circumference will be equal to pi D. And then if you have number of poles, 2, 4, 6, whatever, then you divide it by the number of poles. That will give you tau P, the pole pitch for each one. So that's how you calculate it. Why we need it? I'll tell you now why. Because it's sometimes, I mean, most of the time they give you the flux density. The flux density, it means the flux per volume, per meter cube. So you got to find the volume of the I'm sorry, the area, but the area. So you have to find the area that on the rotor that facing this pole shoe, that where the flux will be intersecting. So how do I find the area now? Now this is tau P, and the length of the shoe is L. So we multiply tau P times L, it gets you the area that's facing this pole shoe. So the area, we call it AP, the area of each pole, will be equal to tau P. You just tau P times L. And if the flux density is given, multiply this density, flux density, by the area, give you the total flux under each pole. If it was given to you directly, just use it. So you have to understand that phi is the flux per pole, not the flux, the total flux per each pole. Now we'll go back to our example here. So it's given average flux density, as we expected, average flux density over one pole pitch is equal to 0.4 Tesla. So that we'll call it phi average. That's equal 0.4 Tesla. So I need to do the process, find that. Well, the armature diameter is equal to 30 centimeters. So you got the diameter is equal to 30 centimeters. So which is, you can write it 0.3 meter. All right. What else? The question is, oh, we forgot the pole shoe is 20 centimeter long. So that's our L is equal to 0.2 meter. All right. Then find the torque. Find the torque and gross mechanical power developed. Power developed, that's RPT, developed in the rotor. When the motor is drawing 25 amps, so that's the motor, and it's taking 25 amp. That's the current of the armature, and it's rotating 1500 RPM. All right. So you need to calculate the developed power and the developed torque. Means what does mean developed torque? The torque that like the raw torque produced of the motor before it go to the shaft and lose, the all mechanical loss. That's the starting, the raw torque produced by it's electromagnetic torque before you go to the real world side, the rotor. Okay. That's the problem. Right. Let's see how it's a very simple one. Even if you think the information not, that's not. Let's think about how to find the torque. We should know the relation between the torque and the power. What's the relationship between power and torque? That's in physics, long time ago. Anybody? It's not DC machine, it's general. The relation between torque and power.
Torque is force times distance.
Torque is force times this. That's right. Yeah, that's the torque. Yeah, power.
Power is like, is that like force, the integral of force over time? Power? Like, is power like force over time? Something is made force.
Let me just write what you said. You say now torque is equal.
Torque is equal to force times distance.
Yeah, that's the definition of it. The relation between torque and power.
So would it be the integral of force times distance?
The integral
Of force times distance?
force time distance. You are saying that, right?
Or the relationship between power?
Yeah, but what is the power? We are looking for power.
I guess we're-
What about the linear motion or translation motion, not the rotation? Okay. That's physics, guys. Physics. What is work? Let's walk step by step. Something moving in a straight line. How can you find the work? Exactly. So if you are having an object and there is a force and then it move a distance x, so the work is equal force time x. And if you like to find just the change of the work, you can find the change of the displacement if the force is constant. How you find the power? Work is like kind of energy, right? The energy work. So what is the relation between power and work?
Integral with respect to time? Integral over time?
You guys memorize rules and formula. Yeah, I want you to understand that physical thing. If I have an object like this button, and then I did move it from this place to this place, I did work, right? In Joule. Maybe if I get you and I ask you to move this thing, you will do the same work, but it took me like 30 seconds, it took you 5 seconds. Who's more powerful? You are more powerful because it took you, less time. So power is like relating work to time. So if you find with respect to time, then you get the power. So the power when you something moving in a straight line is equal force times velocity. All right. Now let's go for something rotating. It will be very similar. Power will be equal to the force will be torque, so velocity will be omega. Omega. And I can prove in the same way. So power is equal torque times omega. And power in translation motion, it's equal force times velocity. So now, if you want to find the torque, you're supposed to find the power. So power, the developed power is equal the developed torque times omega. All right. And by the way, there is a speed here. So the speed n is equal 15 RPM. So you can find omega. So to find omega is equal to pi n over 60. It means pi n over 30. You don't forget that. How to convert from RPM into radian per second. And if you do that, so the power BD is equal TD, developed torque, times pi n over 30. So if you want to find the torque, so the developed torque will be equal to 30 times PD divided by pi n. And we like to make life easy, so we divide 30 by pi and see what the it's like, I think if you do it, it will be 9.55 BD over n. So we to find the torque, and you know the RPM, just divide P by RPM multiplied by 9.55. Now we'll come to the second question. How can you find the developed power? By the way, this power developed by the motor, it's electric. So what is the power in electricity? How you calculate power? Any power? Multiply volts times current. Okay. What is the voltage produced in the armature? No, the voltage. What's the name of the voltage produced in the motor? EA. Yes, the EA. So the power is equal the voltage and EA, and the current in the armature is called the current in the armature. IA. Okay. So now, do you have IA? Yes, you do. IA is given 25 amps. So I know that it's equal EA times IA. And IA is equal to 25, so 25 times EA. But what's EA? I don't have it. So now my job is to calculate the induced EMF or the back EMF EA. How do you find EA? We just explained just before we start the example. EA is equal what? Is equal the constant or machine constant Ka times phi times omega. I have omega already, right? So we have omega. I don't have Ka. I don't have phi. So what's my task now? To find Ka and phi. Do you know how to find Ka? Yes. We just had the equation. We said that Ka is equal to Zp over, I think it was like 2 pi A, right? Yes. And Z number of conductors is given. Number of conductors is equal to 400. Number of poles are 4. 2 pi times A. A is the number of parallel paths in the winding that they are connected. And it's mentioned that it's lap winding. So if it's lap winding, then the A will be equal P. So A will be equal P equal 4. And that will be our Ka. It will be, I think, if you do 200 over pi, you can give me the number if you like, but I can keep it like that. That's the constant. I'm done with the constant. The second variable that I need to find, the second constant, I need to have pi, the field flux per pole. What's given here? It's giving the average flux, not actually, it's the density, flux average density, average flux density per area. So what I'm supposed to do? I'm supposed to find the area AP, and we just explained that. So to find the total flux per pole, that will be equal the B average given to me times the area under each pole shoe. And we already explained that the area of the pole is equal the tau P, the pitch pole, and or the pole one pole pitch times the length of one pole pitch, which is equal to, and tau B, even we got expression for it, right? Tau B, we said that's equal pi G, that's the whole circumference of one circle of the rotor, and then divided by the number of poles. It gave me just the length of the arc under one pole times the length of the one pole. All right. I have the whole information here. The average flux density was equal 0.4 Tesla. So that's 0.4. Pi times D, the diameter was given as 0.3 meter, divided by the number of poles 4. The length of one pole pitch is equal 0.2 meter. So I got the flux. If you calculate it, you'll find it's equal to 0.0188 Weber. So I got the flux phi, I got the constant Ka, and the omega, it's easy to get. The omega will be equal to 2 pi n over 60. I said we can do it like pi n over 30 pi. Keep it like that because I'd like to find the constant. So I got now the expression for omega, for the flux, for Ka. Let me write it now. So Ea will be equal Ka phi omega. Ka is equal to Z P and 2 pi A, and phi and omega is equal pi n over 30. I'll try to get another expression if I know n, I don't know the omega. So I have Z P, that's constant, and they have 2 pi A, and then pi, oh, pi can cancel pi. All right, that's good. So I have only 2 A and 2 times 3 equals 60. Another thing, 60, all right. It's getting simple, 60A. So that will be a constant times 5 times n. So I got another expression now, easy for m. I'm going to call this something, you know, let me call it like K. Well, no, I will put phi inside. I'd like to put phi inside. If phi is constant, to be easy. Right, phi. And I call it K-E-N, like the constant of the EMF, if you know n only. All right, so I did calculate that Ke and n, it's equal 1500. So if you do that and substitute, I got Ea is equal 188 voltage. So I got the voltage of the armature. So now I have everything. I have the voltage of the armature, the current of the armature is given. I can calculate the developed power. So now the developed power is equal Ea times Ia, that's 180, and the current is given 25 amp, and here you go, I got it 4700 watt. I got the power, and I need to find the torque. Okay, let me write back again. The power is equal torque times omega. I'd like to find also expression with n. So Td and omega is equal pi n over 30. So how to find the torque? So the torque will be equal to 30 times Pd divided by pi, and you put n here. And then we calculate this, that will equal to, what was the number? 80 over pi is like, oh yeah, 9.55 PD over N. You remember that. So you can find the torque dividing the power in what? Divided by the speed as RPM multiplied by 9.55, you get the torque in Newton meter. All right. So I did that. So I have 9.55 and the power, it's equal to 4,700 watt divided by the speed 1500 RPM. Then I got the torque 29.9, or you can say almost equal 30 Newton meter. So that's how you get the torque. Did you follow the sequence? So just to pay attention, the machine constant is important to find the EMF or the torque. It depends what's the, it depends on the okay.
So
Yes.
do you always solve for power? Develop for, like if we're asked for both of those in the same problem again, would we solve for power
To find the
first
torque?
again, or would
Yes.
we solve for torque and then solve for power?
No, solve for power and then get the torque.
Okay.
Because the torque is as a motor. When you work at generator, will be the other way, be the opposite way. You have the torque, then the power. Because we prime mover. But now we are producing, and the motor producing the torque. So first it comes from where? From the power. Yes. Now let's go how to represent the DC machine as a circuit so we can analyze it. And this is the fun part. That's in front of you here you have like two pole, north and south. That's the field. And by the way, there are windings. You see, when you see the dot, it means that there is wire coming out. When you see X or cross, it means that wire coming in. So, I mean, that's annoying. Okay. When, where did it go? Okay. So, this one, like, I mean, you have a winding here. Of course, not winding. You can have many. And then you continue on the other side, many. And then here you go, you have the supply. So this field can be represented by a separate circuit. And that's what I did. That's the field winding. Because, I mean, next week you're going to do the experiment for the dynamometer with coupled with DC machine. So you will have the DC machine and then you will see, I mean, some connection with the field winding, armature winding. So I want you to be familiar with that. So that's the field winding. And usually we connect the field winding with some rheostat. Rheostat is like a variable resistor. Why we do that? So we can adjust the field. How we adjust the field by that? Because as you know, that the field current will go in this winding. The flux produced by this field winding depends on the magnitude of the current, IF. So you can say that the flux is proportional to, of course, if you don't have permanent magnet, DC motor, if we have something like that, excited externally. So you will see even in the lab, there is a winding and there's a rheostat variable resistor, and then you will bridge it. So you connect them so you can control the field current. And usually you put the rheostat in the beginning when you start the experiment on the high, on the greatest value of the rheostat, like it's like 600 the maximum till zero. So you put on 600. So when you start, the current will be small and the flux is building gradually. That's very important. So that's the representative of that. RF, and RF is the total resistance. When I'm saying RF, it means the total resistance in the field circuit. And if we have supply separate to the DC machine, we call it separately excited DC machine. It means that the field is connected to special source, DC source. And the armature here, the rotor has a winding called the armature winding. I got it out of the machine. So what's that? Since it has winding, it has a resistance. So this resistance, I'm going to call it armature resistance, or the resistance of the armature wire, RA. And why I'm doing that? Because there is back EMF produced. So you will have here, that's your EA that we have been talking about calculating. It's EA here. Why you call it back? Because you are applying voltage here across VA, that's the voltage across the armature, and then back EMF producing the winding because it's moving. So for example, if you have 200 volt, maybe you have like 150 opposing it, okay? So that's the equivalent circuit of the armature. And if you keep the armature and the field circuit separated, what does it mean separated? It means like each one has its own DC power supply. We call it separately excited DC machine. All right. The way you connect the field and the armature, it will produce new type of DC machine, and each one has a good or a specific application. For this one, the separately excited, you see the field separated from the armature. Everyone has its own supply, their own source. That's why I call it separately excited. When you connect the field in parallel with the armature, so you don't need two supply anymore, only one supply. And it's connected in parallel. The field is connected parallel. We call it shunt excited DC machine. Shunt excited means parallel. They have only one source. That's, in this case, we call this V terminal. All right. And it's very important to know you have EA and you have RA. V terminal, it's the, like if you have a battery, 12 voltage, that will be the terminal. But EA is not equal to VT except only in one case, if you don't have load. If there is no load and the current is IA0, you have to keep in mind that. And also another thing, the voltage across AA, that's the armature voltage, as I show you here, the armature voltage. But that's okay. The armature voltage will be equal to the terminal voltage in one case, if you don't have external resistance here. They use in the old days to put resistance on the line of it, so you can control the speed. But of course, I mean, they found this is like losing power, so they don't use anymore. But you got to know it because maybe you face it. So if there is resistance in series connected here, so the armature voltage will not be equal to the terminal voltage. All right. And of course, if you have the current here, I terminal, or call it I, so it will be distributed. The current will go to the field, we call it IF, and the current going to the armature, we call it IA. So I will be equal IF plus IA. And then if you connect in series, you connect the field and the armature in series, so the current going in the armature is the same current going in the, so I will be equal IA equal IF. Dealing with series DC motor, and you're going to do experiments that very dangerous. And I'll tell you why when we get to it. Very dangerous. Because the field current is the same armature current, and then what's happened, I mean, if there is some kind of starting from 0 to another value, we are going to discuss this. It's not the issue, but this is series motor, and it's good in traction application, vehicles and things like that. And then there is compound. Compound connections, like you can make series and parallel to them. There is one part of the field connected in series and one connected in parallel, and there are two kind of compound. One called short and one called long, and it depends if you see here, for example, for the long one, that's the external power supply, the terminal voltage VT. Part of the field connected in series, as you see with the armature, and the other part in parallel. But still the voltage applied to both groups. That's one kind of compound. So compound means you have both series and shunt. Means the field is divided into two groups. One group of the field is connected in series to the armature, and one group connected in parallel. But observe in this one, because we have two types of compound. This connected in series, but the voltage VT across this combination the same across this one. Look at the other one. So if I sketch that, that's the armature, and then one point here, this one doesn't change like this one, but this one is not in series with it. No, in this way. That's field. For example, that's RF1 and that's RF2. Of course, now we see the difference. The terminal voltage is not across RF2. It will be part on RF1 and part on the armature. That's the difference. But this one, you have the DC and you have the field here and you have another field here, and the terminal voltage is the same in both groups. Okay, that's the different compound. Everyone has like its own application, but in general, what are the main types of the DC motor or machine? Because generally the same thing. According to the connection of the field, you have separately excited, shunt, series, compound. These are the units that I will keep it in the folio. It's very important, the unit to use, because I mean, not everybody using the torque in Newton meter. Maybe in Europe they do that too. They do also here, but sometimes you use like a foot pound. So I give you here the conversion when you need it. And also something, I mean, usually the DC machine, the DC motor, they put on the nameplate the power. And the power, usually if anything moving, rotating, they give it a horsepower. So to solve or to analyze things, you got to be able to convert it from horsepower to watt. So it's like 1 horsepower is equal 746 or 47 watt. I put also the information here for the horsepower and the watt. That's the relationship given. And I give you two formulas to make life easy, like two formulae. There's one and there's two. This one, how that I just explained to you just in the previous example, the relationship between power of the shaft, the torque, the speed, when in watt Newton meter. Use this equation. Power is equal T times N. N is the same for both equations. RPM. You divide it by 9.55 to get the power in watt. And the torque given in Newton meter. All right. That's like SI system. English system, if speed doesn't change, RPM the same. The torque foot pound the power horsepower, this equation will work with you. So Tn divided by 52. I approximate this number, and I used it when I was student. I had this number like 52. It's easy. It's not exactly 52. It's like 52, 51 something. I mean 52. It is to remember 52. Okay. So these are the two formula that you are going to use when you want to change from. Because it was painful for me as a student. I was just looking for it, I mean, find one problem in foot pound, one in watt, and I searching. So I just put it for you here in a table, so it'll be easy. Now, let's go to one problem. I hope that we can be able to finish in 8 minutes. That's problem number 2. I was optimistic. I have like 5 examples of that. A DC motor is connected to a source of 150 volts. I'm talking about, of course, I'm going to explain what's coming today and next lecture. That will be separately excited DC machine. So the DC motor is connected to source 150. That's the terminal voltage, right? And its armature resistance, which is RA, is equal to 0.75 ohm. The armature generates 40 voltage when running at speed of 400 RPM. That's interesting information. So the armature generate what? Voltage. What you call this voltage? Yeah. Okay. You guys like yeah? Huh? Yeah. Yeah is equal 40 when the speed equal 400 RPM. All right. Let's start now. Calculate just the only information. The starting current. We want to know the starting current. When you start the machine, what the current will take. If you look at the circuit, we just explained that you can add the resistance here. Doesn't matter in series. That's your RA, and the current here is going IA. And if separately excited, that's the supply you're going to have, V terminal, all right? And the voltage produced at the armature EA. So if you look at the circuit, you see that the terminal voltage, and by the way, the terminal voltage is the same VA in this case, because there is nothing between the power supply and the armature. So VA or V terminal is equal to EA plus the drop voltage here will be in series RA IA. All right. That's the equation of the circuit. Very simple one, Ohm's law. Remember what we're asking for. You want to find the current at starting. Well, so there is a relationship always between the EMF and the speed. Always. Speed. So what happened in the starting? What is the speed? At starting. When you start the machine, what is the speed? Huh? I can. No, I'm talking the speed. Speed, not in volts. Yeah. When you start the machine, what is the speed? What is the speed when you start it? Zero. Yeah. Don't think about it. So if the speed is zero, what is EMF? Zero. Why? Because the proportion to it. Yeah. Because we know that EA is equal KA phi N. I mean omega. So if this is zero, that's zero. So at starting, VA will be equal to 0 plus RA IA at starting. So the current simply will be equal to VA divided by RA. So VA is equal to 150. And RA is equal to 0.75. Then you get the current will be equal to 200 amp. And always the starting current is really high, because if you have this term EE there, then you will, to find IA, you will subtract V minus E, and they are so close, the current drop dramatically. So that's why we're going to talk about techniques, how to start DC machine, not to have this high current, 200 amp. Well, I'm going to see, the current when it starts. Well, the second, the back EMF when the motor runs at 800 RPM and we're running at 1200. Let's just get one. I will solve for one and you get the second. We want to find the voltage when it's running at 1200 RPM. All right. Oh, I don't have space. Okay. So now the information, it will help me this one. It will help me this one. Why? Because I know there is a relationship between the voltage and the speed. So if I do, let me just erase this thing. Don't worry, I have it written and I'll publish it. So we know that EA is equal to KA phi omega and the same thing. So EA, if this is constant and it's constant now, so EA is proportional to omega, or you can say EA is proportional to the speed. So accordingly, you have EA2 divided by EA1 is equal N2 over N1. I can write that. All right. EA2, I don't know it. EA1, it was given 40. And the corresponding speed was 400 RPM. And I need to find when it's 1200 RPM. So just it's easy. So EA2 will be equal to 1200 times 40 over 400. So I get 120 voltage. 120 voltage. So to get 1200, the EA will be 120. I just want to tell you about, it's not required, but I'd like to calculate the current in this case. Just to compare it with the starting current that we got it was 200 amp, right? So if you want to find the current at this speed, can you? Yes, because the voltage is equal to EA plus RAIA. So look at that now. IA will be equal to V minus EA divided by RA. The voltage is constant in the source, equal 150. And EA in this time is 120 divided by RA, which is equal to 0.75. So in this case, 150 minus 120 will be equal 30. And this is like 3/4. So it'll be 40. So the machine, when it starts to work, it only takes 40 amp. When you start it takes 200. Starting always like hard.